Hi, my name is Alex, and today I'm going to talk about MobileGravity, a mobile simulation of a high range of weight in virtual reality. I present this work on behalf of my co-authors Johannes, Tien-Julian, and Niels. The perception of weight plays a key role in how we interact with objects. When we lift or hold objects, we inherently sense the weight to understand the physical properties. This affects the force we apply, our movements, and ultimately our interaction. In virtual reality, the perception of weight is distorted, as the sense of vision is stimulated separately from the tactile and kinesthetic senses. When holding objects in VR, users sense the weight of the input device, which is typically different from the weight of the object seen in VR. This mismatch in weight, as demonstrated by the video on the right, negatively affects realism, enjoyment, and game experience. Providing realistic weight sensations is therefore a key challenge for the advancement of VR. To address this, researchers have shown increased interest in exploring novel interfaces that simulate the sensation of weight. Lim and colleagues reviewed these approaches and concluded that simulating weight forces remains an unsolved challenge. It requires a simulation of a multitude of complex, tactile and kinesthetic information to generate realistic and robust weight force. So it doesn't seem viable to imitate the sensation of gravity. However, we could provide the sensation of real gravity forces by changing the weight of equipment. As a result, multiple research prototypes were introduced that utilize liquid mass transfer to convey weight in VR. These are based on the integration of liquid reservoirs in handheld or body-worn devices. To change the weight, external reservoirs pump liquid in or out of them. Unlike other methods, this approach allows to provide real gravity forces instead of simulating only aspects of the sensory information through which we perceive weight. Each of these prototypes demonstrates solutions to individual objectives, such as simulating wide ranges of weight, applying weight changes at high speed, preserving mobility, stimulating multiple body parts, and the ability to render multiple centers of mass. However, it becomes evident that while solutions exist to address individual objectives, they are unfit to satisfy all of the criteria simultaneously. In particular, the initial approach to preserve mobility, varying the hardware along with the water supply in a backpack, limits the complexity, weight range, and pumping power, as these approaches aim to reduce the overall weight of the structure and therefore incorporate weak actuators in low weight capacities. Devices that were able to meet multiple other objectives, in contrast, lack mobility through the added weight burden. So there's a clear trade-off between mobility and performance for these devices. But being able to walk around freely in VR is essential for effective locomotion and reducing cyber sickness. Also, a broad range of VR experiences just require unhindered movement. For instance, VR fitness training or room scale games or motion-based learning applications. To address this, we developed MobileGravity. Here's how it works. It changes weight through liquid transfer, but decouples the weight-changing object from bulky and heavy components. This allows the user to walk and turn around freely. And yet enables changes of up to 1 kilogram and 235 grams per second, making the device more performant than previous approaches. MobileGravity consists of a mobile handheld proxy object and a base station that can change the weight of the proxy. Central to our design is the integration of dripless quick disconnect couplings. These are fittings that automatically cut off the water flow when disconnected. They allow to connect and disconnect the handheld device to the base station whenever its weight needs to change. Water can then be transferred between the two reservoirs. The male coupling is integrated into the handheld proxy. which has a capacity of 1 liter. Its rotation and position is tracked using an HTC Vive tracker. The proxy features a secondary handle positioned perpendicular to its primary handle. This enables users to perceive the center of weight at various positions. For instance, in this case of this blowtorch at the front. The female coupling is embedded in a socket at the top of the base station. The socket has a slope towards the fitting in the center, so that the proxy object can snap in smoothly. This is then detected by a limit switch. 2 solenoid actuators separate the 2 units again, as you can see in this video. A bidirectional pump initiates the water flow. And a control unit controls the components using an Arduino Micro and 4 relay modules. To test our system, we created a virtual world in Unity. We chose a virtual workshop setting to feature objects with a broad range of weight in a coherent scenario. In this scene, users can build a bird box in 6 steps using a paint roller, a stapler, a hammer, a hacksaw, a blowtorch, and a cordless drill. Each step requires the user to first pick up the respective tool from the tool bench. Users then have to take the tool to the work table. There, they use the virtual tool to carry out the work required at the current stage by moving it in the same way as they would a real tool. They then return the tool to the bench, which initiates the weight change and starts the next step. Users then proceed with the next tool until the 6 steps are complete and the birdhouse is assembled. We conducted a study within subject design in which 30 participants completed this scene. We used system as independent variable to compare MobileGravity with a regular HTC Vive controller. We found that MobileGravity significantly enhanced the participants' weight perception. We also found significantly higher scores for effectiveness, which assessed whether participants experienced different weights during the task. And we found significantly higher scores for haptic realism, which assessed if the weight differences between the tools felt the same as in the real world. This indicates that participants perceived the weight to have changed according to the different tools. This came with a positive impact on the overall experience, as we found large effects on realism and enjoyment. This shows the system's ability to simulate objects of a high range of weight in mobile scenarios and demonstrates the value of rendering object weight for a realistic VR experience. Apart from the demonstrated application, we provide further use cases for MobileGravity. It can be used to simulate heavy and lightweight game items, for instance in this co-located multiplayer setting. It can be used to simulate different avatar weights and room scale setups. Or it can be used to change intensities of VR workouts. So let's conclude this talk. Conveying weight in VR is a major challenge. And previous approaches came with a trade-off between mobility and performance. MobileGravity addresses this by decoupling its weight-changing object from bulky and heavy components. This enables a mobile simulation of a high range of weight. We showed in the study that this has a positive impact on realism and enjoyment. Use cases include VR training, games, VR workouts, and avatar weight simulation. And with this, I conclude this talk and welcome your questions. Thank you.